All right. Yeah, turn in, if you haven't, turn in that problem. And I'm going to continue. I want to get through the last series test, which is the root test. This test doesn't come into play a whole lot, but you just need to know it's there. If you look at the little comments on your cheat sheet thing, it says that this is useful if your sequence involves nth powers. So if your sequence itself has nth powers, you might want to think about this, all right? So what does the test say? We have some series. We can't figure out if it converges or diverges. We take a look at the sequence. We take the limit of the absolute value of the sequence, and then we take the nth root. And if this limit turns out to be a number that's less than 1, it converges. If it's greater than 1 or infinite, it diverges. So let's just take a look at an example.
Can we use this as alternating series too?
Pardon?
Can we use this as like an alternating series?
Yes, this will work with any series, alternating or just a regular series. So here's an example. Sum n equals 1 to infinity, 5n plus 1 over 11n minus 1, all raised to the nth power. So you may look at this problem and you may say, okay, hey, look, I've got something to the n. Anytime I saw n as a power, I was thinking geometric series, except for the fact that the number inside here, well, it's not a number. It's not fixed, right? This isn't an r. So that's not going to work. We say, oh, wait a minute, though. The root test says that if we have an nth power, we should use the root test, right? This is an nth power. So what I'm going to do is apply the root test. I'm going to take the limit as n goes to infinity of the nth root of the absolute value of this. Now, this is always positive, isn't it?
Yes.
So I don't need to take the absolute value, right? Positive number, raised to the power, still positive. So I'm going 5n plus 1 over 11n minus 1 to the nth power. And do you see the usefulness of this? Yeah, the nth root of nth power, those basically kill each other off. So nth root and that go away. So you have limit n goes to infinity of 5n plus 1 over 11n minus 1. And remember, we're doing a limit here, right? We're not doing a sum. We're just taking a limit, and we get infinity over infinity. So L'Hopital once, so you'll get 5 over 11. And that number is less than 1, right? Which means that this series converges. So therefore, this up here converges. That's pretty straightforward, huh? If we didn't, you might say, well, you know, that seems too easy. Well, if you didn't have that root test, you would try something else, and it would get pretty ugly. I mean, if you tried ratio test, it would be pretty nasty. So this is very convenient when we see nth powers, all right? Now, did I assign all the homework out of this section?
You did 6 to 30. 6 to 30.
Yeah. Let me just double check that to make sure that I'm done with that. Oh yeah, there was another one I wanted to do. Where was it? Where was it? Where was it? Here we go. All right. It's number 38, actually, in the section. I want you to try and go through all the way to 39. Okay? So the final assignment is like 3 through 39. Okay? But I'm going to look at number 38. Now, the reason why I'm looking at 38 is because we have not seen something like this before. So here we go. 38 says you have 2/5 plus 2 times 6 over 5 times 8 plus 2 times 6 times 10 over 5 times 8 times 11 plus 2 times 6 times 10 times 14 over 5 times 8 times 11 times 14 plus dot, 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 dot. And the question is, does this converge or diverge? All right? If we're going to try and do this problem with a test, then we need to find a summation formula for it, right? And then we can apply a test. So we need to see, is there a way we can come up with the a sub n that goes into this summation? So let's start looking at some patterns. What sort of patterns do you see here?
It's adding 4 on top and 3 on the bottom.
Yeah, each time you do this, you get 2, and then you add 4 to that, you get 6, and you multiply it. The next time it'll be 2, 6, and then add 4, you get 10, so multiply those 3. Next one, 2, 6, 10, you add 4 more, you get 14. Understand? On the bottom, you're adding 3 each time? Okay. So I'm going to start my sum at 1, and let's see, how could you write this? I want some feedback from you, because you've never had this before, and you're going to have a problem trying to do it. Do you all see the trouble?
Yes.
What's the trouble?
That is like going up by 4, but it's not.
It's multiplying, right? Yeah, that's a trouble spot. So let me see. How could we write it as a sum? I mean, that's what we have to figure out. Can we do this? It's going to be a notation we've never used before. Let's try and come up with a general formula. Okay, maybe just come out here, go dot dot dot. What would the nth one be? Can you tell me what the nth one would be out here? Of course, it's going to keep going, right? Because it's infinite. What would the nth one be? Remember, this is the first one. This is the second one. This is the third one. This is the fourth one. Keep going.
N plus 1 on top. And bottom 4 plus 2.
Okay, maybe if we go backwards. At the first one, we just have 2 and 5, right? Okay, at the second one, we have 2 and 5 again, but now we've attached to it through multiplication 2 plus 4 and 5 plus 3. So we've added 1 3 to that. On the next one, we have the 2 and the 6, the 5 and 8 like the one before, but then we've added another 4 on top and another 3 on bottom. Yeah? So really trying to see how I can get you to see this. Let's try and take it a little slower. Can you just create this? Can you just create that? Forget the bottom for now.
2.
2, the next one is 2 times what? 2 plus 4? What's the next one?
Plus 4.
Hold on. 2 times 2 plus 4, that's your 6, and then what? Plus 4 again. Could I write that as 2 plus 4 plus 4, or 2 times 4? I know that looks weird. But see, I've taken 2, I've added 4. I've taken 2, I've added 2 4s. The next one will be what? 2 plus 4, 2 plus 2 4s, 2 plus 3 4s. Are y'all following me or not?
Yeah.
This is what I got when I did what? When n was 1. This is n is 2, right? N is 3, I'm here. Are y'all following me? When n is 4. So what about when n is n?
2 plus 2 times 2 plus 4 n
plus 1?
Wait, say again?
2 times 2 plus 4
2 times 2 plus 4n. Where's this 4 here? I don't see that 4 here. Okay, so do you see how difficult this is? So I think what would be more, I guess, would get us there faster, because we could play with this for the rest of the class until y'all come up with it, right? Is to just show you, perhaps, and then once you see it for the first time, you'll be like, okay, got that. All right? Let's just see if that works. Do you agree that this is 2 times 6 times 10 times ... all the way out to 2n, or 4n minus 2? Okay, so let's try it. Let's try that formula right here. This means I'm going 2, 6, 10, and I'm adding 4 each time until I get out to what? 4 here, so 4 times 4 is 16. 16 minus 2 is 14. Is that my last one? Yes? What about when n is 3? We go 2, 6, and I stop at what? 3, 12 minus 2 is 10, so I stop at 10. Do you see that? Does it work for this one? I go 2, and where do I stop? I stop at 8 minus 2, stop at 6, right? And then if n is 1, I go 2, and then what? Stop at 2. So I should stop right where I was. See, there's no clean way of writing this, all right? There's no clean way that we can write repeated multiplication. All right? So we just come up with this ... formula. See, now maybe you can get the bottom one with that idea. These are all multiples. These are all going to be multiples of 3, right? 3, it's 3n, right? Plus 2, good. So it's going to be 5 times 8 times ... all the way out to 3n plus 2. Perfect. That's it. So if n is 1, where do I stop?
3.
At 5. So I just have 5. If n is 2, where do I stop? 6 plus 2, 8. So I go 5, then 8. The important thing is that this stuff in front, ... means I have to keep multiplying until I get to that number. It's not just that number itself. Understand? So in my summation, let me just write this down. Don't write this. This would not be correct. Do you agree? This would not be it. Because what that's doing is that's grabbing only the last number. It's not telling you have to keep all the other numbers each time you go. So I need to write 2 times 6 times 10 times ... to wherever I stop over 5 times 8 times, 11 times ... all the way to where I stop, 3n plus 2. Is that all right? Now you'll be able to practice this on your homework on number 37, okay? There's another problem that you can look at and try and come up with the formulas. All right, does this converge or diverge? Well, what would you like to try? You can try the n term test, but that's a limit we've never dealt with in our life before. Because what's happening is as n goes to infinity, those guys are actually taking off. This is getting longer, isn't it? As n goes to infinity. It's not as simple as just doing n term test on that. Because this would be L'Hopital, right? Yeah. You've got all this other junk.
Could you do the ratio test, but like instead of having all the numbers in front, just put a plus because you know all those numbers are going to be positive?
Yeah, let's do the ratio test. I'm on board for that. Let's try it, okay? Let's try the ratio test right now. The ratio test means we're going to take a limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, right? That's what the ratio test is. If that turns out to be a number less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, the test is inconclusive, right? All right, so what is, and this is a very tricky part right here. What is a sub n plus 1?
2 times 6 times 10.
It's 2 times 6 times 10 times dot, 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 and then I replace my n with n plus 1. The n, you needed to do this on the take-home quiz, which is due if you have it. You have to turn it in. You're replacing n with n plus 1, so I have to replace that n with n plus 1. Real quickly, what's 4 times n plus 1 minus 2?
4n plus 2.
4n plus 4 minus 2, so 4n plus 2. So the last piece here, and please give yourself a little room. Actually, I'm going to give myself a lot of room. I'm going to move this. I'm just going to move this limit over a little bit. This is equal to, sorry, I'm doing the ratio test. Yes, it's the limit as n goes to infinity of 2 times 6 times 10 times, and we said dot, dot, dot. We said the last one would be, what? I forgot. 4n plus 2, agreed? Over, I left space here intentionally, all right? Over 5 times 8 times 11 times dot, dot, dot. What's the last one here?
4
So you have to figure out what is 3 times n plus 1 plus 2. So that's what I get when I plug in n plus 1 there, which is 3n plus 5. Is that good? Just distribute the 3 through. 3n plus 3 plus 2. 3n plus 5. Are y'all on board or not? Yes? Okay, over what? 3, yes, I did. Plus 5. Thank you. Over a sub n, which just write these out again, right? And it stops at 4n minus 2. And then over 5 times 8 times 11 times dot, dot, dot to 3n plus 2. Y'all get that?
Yes.
Now, this fraction is really going to flip up and come up here like this, isn't it?
Yep.
Reciprocate and come up. I'm going to do that. So I'm going to move this absolute value. I'm going to say times, and I'm going to flip that fraction over and put it up here. 5 times 8 times 11 times dot, 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 all the way to 3n plus 2. And then 2 times 6 times 10 times dot, 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 4n minus 2. Understand what I've done? That's all not there anymore? Now, I think it's obvious that we get some cancellation here, right? The question is, how much cancellation do we get? So, is it all gone? No. That's why I left this blank right here. If this is what I get when I plug in n plus 1, what's sitting right in front of it?
4n.
What I get when I plug in n, right? Is the one right in front of it?
Yeah.
Which is, what, 4n minus 2? And if this is what I get when I plug in n plus 1, what's the one right in front of that?
3n plus
3n plus 2. And if you do it like that, then you have lots of cancellation. But not everything, right? Not everything goes away? Let's see. 2, 2, 6, 6, 10, 10, dot, 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 everything. And this 4n minus 2 and this 4n minus 2 go away.
2. 3n plus 2.
The 5, 8, 11, 5, 8, 11, everything in here, the 3n plus 2 and the 3n plus 2. The only thing left is what? 4n plus 2 over 3n plus 5. So I'm left with the limit as n goes to infinity, the absolute value, although we don't need it, 4n plus 2 over 3n plus 5. And now you can use L'Hopital's rule, because it's not a bunch of dot, dot, dots anymore. And this is 4/3. Which is bigger than 1, which means what? It diverges. Therefore, the series, right, diverges. I'm not going to write the whole series out again, but the one that we were looking at diverges. Okay. Is that all right? Mess with the homework problems. You'll have a little more practice with that. All right. Start 8.5. Power series. All right, so let me show you what a power series looks like. Excuse me, damn it. A power series looks like this. Notice it starts at n equals 0, not n equals 1. Of C sub n, that's a C sub n, x to the n, and that's it. Now, let me tell you what C sub n is. C sub n are constants x is a variable. So look, if I cover up the x to the n power right there, if I cover that up, that's what we've been doing, except I'm calling it C sub n instead of a sub n, all right? And I'm starting at n equals 0 instead of n equals 1. But now we're introducing, next to each one of those terms, each one of those numbers that we're getting in the series, we're putting a power of x next to it. So like, if I let n be 0, I get c sub 0, x to the 0, plus now c sub 1, x to the 1, plus c sub 2, x to the 2, plus c sub 3, x to the 3, plus dot, dot, dot forever, right? They call this a power series because it is a series, right, that has powers of x in it. You've seen some power series before. I'll give you an example. When we studied functions in college algebra, this is a power series, but it's a finite power series because you start off, right, you have a number in front of x squared, a number in front of x, a number by itself, right? If I flip this order around and write it 4x to the 0 minus 3x to the 1 plus 1x squared, do you see that that follows this format right here? I have a number, in this case, c sub 0 would be this one, right? C sub 1 would be this one, and c sub 2 would be that one. Understand? So if you cover all the x's up, 4, negative 3, 1, those are just numbers. That's a series of numbers, right? That's what we've been studying. We're just tacking on now powers of x that continually increase as we go. Understand? No questions? All right. If we fix a value for x, okay, because I have not told you what x is, right? I have not told you what x is up here. It's just a variable. But if I tell you, okay, look, hey, everyone, x is going to be whatever. I give you a number. Then this is just a series with just numbers in it now, right? And haven't we been studying whether or not those things converge or diverge? So by itself, as it appears, a power series, you don't know really right now whether or not it converges or diverges. But if someone gives you an actual value for x, if we fix it, you should be able to determine if it converges or diverges, right? So if we fix a value for x, we should be able to determine if it converges or diverges. You agree with that? If it converges, that means it goes to a number, right? If it diverges, it means it diverges and it doesn't go to a number, right? So with that in mind, I'm actually going to come in here and add one more thing to this, which is kind of the big deal. I'm going to define this to be a function. I'm going to call a function f of x equal to that infinite power series. Now remember things about functions. One of the most important things about a function is its domain, right? That's the things you can plug into it and the things you can't plug into it. So for example, when we looked at functions back in the day, I'm giving you examples. Let me give you this one, x cubed plus x. Can you plug any number into that? What's the domain of this? All real numbers, right? There's no problems. You can give me any number, I can cube it, I can add it. It's all good, right? So the domain of this is all real numbers. So domain here, I'm going to say double struct R, all real numbers. Is that okay? What about another function as an example? Square root of x. Can you plug anything you want into that? No, you cannot plug in negatives, right? So the domain of this, you would say something like all x's must be greater than 0, right? You could say that in many different ways, interval notation, set notation, but the idea is that x has to be positive. It can also be 0, pardon me, because the square root of 0 is 0. So, that okay? One more function, f of x equals 1 over x.
Can't be 0.
Domain of this is everything except 0, right? So x can't be 0. So we are familiar with the idea that if someone gives us a function, we can start talking about its domain, the things that can and cannot be plugged into it, right? So if I come in here and I say, hey, take a look at this power series right here, that's what we're calling it. And if I define that to be a function, then guess what the domain is? Take a guess as to what the domain is.
Greater than 0.
Okay. X can't be 0. What did we say about this sum? If someone fixes an x value, we should be able to determine if it converges or diverges. What if we say that its domain is every value of x for which it converges, and the things that are not in the domain are all the values of x that make it diverge? Does that make sense to you?
Yes.
That's how we define this function. Here it is. The domain of this are all x values which make it converge. What I'm trying to get you to see is that it makes perfect sense to define a function to be an infinite power series. And I'm just saying, hey, look, if you plug in an x and it diverges, well, then that x isn't in the domain. It's not defined there. If you plug in an x and it converges, well, then that's part of the domain. So this function has things that possibly work for it that you can plug in and it makes sense mathematically. I think it might be good if we just do an example, like show you your first power series. That's the general form of a power series, but let me give you a specific one. Okay, example. Let c sub n equal 1. What does that mean? You remember that symbol? No? For all. Did y'all notice in that formula that we had, right, this was it right here? Do you notice that for any power series, x to the 0, x to the 1, x to 2, x to 3 is always the same in all of them? The only thing that really changes is the what? The constants in front, right? That's the only thing that controls a power series, is the number in front of each of the powers of x. And so what I'm doing is I'm saying, all right, well, let's look at a very, very basic power series. It's the power series where all the constants in front of the x's are 1s, always. So it doesn't change. So we're looking at this. Sum n equals 0 to infinity of 1 times x to the n, which is x to the 0 plus x to the 1 plus x to the 2, so on and so forth, forever and ever. Which is really 1 plus x squared plus x cubed plus forever. Please, somebody save me here. See if anyone can see it. What does this look a lot like? Come on. I know it's in there. Yes, very good. That's a geometric series. You can almost tell by this formula. Look, if I were to write this out right now, let me remind you of what a geometric series looks like. This was one form of it, right? That was one form for the geometric series. If I tell you a is 1, then it becomes this, right? And if I say, hey, instead of using the letter r, let's use the letter x, then it becomes this. Right? So this power series is actually an example of a geometric series. When would this converge? When would this particular power series converge? Well, when would the geometric series converge? When the absolute value of that r is less than 1. So when would this power series converge?
When x is less than 1?
When the absolute value of x is less than 1. So this right here, I didn't define it. Let's put f of x equals this in front. This right here, f of x will converge if the absolute value of x is less than 1. Why? Why? It's geometric, basically, right? It's a geometric series. Not all power series are geometric series. This was a specific example. If you let all your c's be 1s, then it is a geometric series. Questions?
Looking at that series, is there a point with x equals less?
Is there? No, we get to control the x. See, this is a function, right? And I'm saying I'm going to plug in a value of x. It's going to spit out an answer, hopefully. There are some values of x I can't plug in, though. The values of x that I can plug in are the values of x that make it converge. Any value of x that I pick, if the absolute value of it is less than 1, this thing is defined. This series is defined. I don't know if I'm answering your question. I don't even know if you're asking a question.
Oh, what is an example of something we can plug in to get it to converge? Because it just seems to be an ever-increasing exponential.
1/2. So let's try it, okay? Let's actually do this. So this function will converge if the absolute value of x is less than 1, right? Or another way you could say this is that the domain of this function is anything in this interval. Doesn't that mean the absolute value of your number is less than 1? If you're in between -1 and 1? Isn't that what that means? So if you give me a value that's in that interval, like 1/2, then this becomes n equals 0 to infinity of 1/2 to the n. And again, that's a geometric. A is 1. Absolute value of r is less than 1. This converges to, what is the formula? a over 1 minus r, so it'll be 1 over 1 minus a half, which would be 1 over a half, which is 2. That would converge to 2. Make sense?
Yep.
And so really what I could do now, if I felt like it, is I could really go back to college algebra. I could say, okay, look everyone, this is x, this is f of x, and I can start plotting points. If I plug in 1/2, where's the y coordinate? 2. Understand? And what if I plug in 0? Yeah, I can plug in 0. What's 0 plus 0 plus 0 forever? 0, right? So I'm here. And what if I plug in 1? It's undefined, right? This is not defined because it would diverge. And if I plug in anything -1 this way, it would diverge. So really what I'm saying is that the graph of this power series, the graph of this function, lives between -1 and 1. And I could continue to plot points, couldn't I? It should be a nice function in here, though. Are we good, or you following what we're doing? Let's get one more point, just for fun. Let's do, you want to do -1/2? So that would be 1 over 1.
But it's absolute value.
The absolute value of the number has to be less than 1, right? But in this formula, r would be, or x would be -1/2. So the formula is still a over 1 minus r, so it would become minus -1/2. So that'd be plus a half, so the bottom is 3/2. And you flip it to become 2/3. So here you're at 2/3, somewhere around there. And then if you had the time, and you know, you could plot the whole thing, and you would have some picture in there. Got it? Okay. Let's move on. Let's look at now what we call a general power series centered at a different point. So let me put the definition up. So we're going to look at a new formula. It's going to look very, very much like what I just put up on the board with one small tweak to it. It's going to be sum n equals 0 to infinity c sub n x minus a to the n. So what's the difference between that and the previous? Yeah, I didn't put f of x, right? But this is, instead of x to the n, it's x minus a to the n. Do you remember what, if you had a function, right, back in college algebra, like we knew what x squared looked like, right? But if I had another function and I said x minus 2 squared, what did that do to the graph? This would shift it to the right 2 places, right? And if I did x plus 2 squared, that would shift it to the left, right? 2 places. So what I'm doing is I'm taking this power series, which we said a second ago could be looked at as a function, and I'm just allowing us to move it around, to move its domain around, really. Shift it left and right, if we want to, all right? This is a general power series. We say about A, or we say centered at A. You'll hear me say it both ways. So let's look at some conditions here. All right, let's look at this right here. What happens if x is equal to a? Remember, we're almost looking at this as a function, right? Like f of x. I want you to get that in your head. We're trying to look at this like a function. What would happen if x was a? You would get 0, wouldn't you? Then this is the sum, n equals 0 to infinity. That's 0, 0, 0. They're all zeros, and that equals 0. Therefore, it what? Converges? What if x is not a? Well, then a whole bunch of shit could happen, right? I mean, you could have a lot of things happen. If x is not a, then that's a number. And that number is raised to a power. And the stuff out here, remember, this is numbers that might be changing as we go. So if this happens where you're not looking at x equals a, then we must check. Okay? We must check. And that's going to be the challenge for us. Our question really for the rest of this class is, here's a power series. Does it converge or diverge? What makes it converge? What values of x makes it converge? Another way of saying that is, what's the domain of this function? So let's take a look at this power series. First example. Second. We did one already, right? Here's a power series. The power series is sum n equals 0 to infinity, n factorial times x to the n. For what values of x does this converge? Can someone tell me right now, right away, a value of x where it converges? Give me a value of x which definitely makes that thing converge. 0. Right? 0. Because this is really, if we look at this as a general power series, isn't this sum n equals 0 to infinity, n factorial, x minus 0 to the n? Right? And therefore a is what? 0. So if I let x be 0, we get 0, and 0 to any power is still 0. So it's just adding 0 up forever, which is 0. And that's convergent, right? Okay. That's not the part that's interesting to us. What's interesting is there any other value of x that I can put in there that would make it converge? Well,
So a is always 0?
what's that?
And for that, a is always 0?
If you ever see just x by itself, a is 0.
Okay.
And just think about it. If I let x be 0, 0 to any power is 0, it's all 0. Everything's gone. All right, also pay attention. This is now our C sub n. Do you all see that? Our C sub n is changing now as we go. Well, how do we determine if things converge or diverge? This, right? But we never had the x's in there before, did we? Which of these tests is useful when we see powers and factorials? The ratio test, right? The ratio test. And I told you that was going to be an important one, right? So what I'd like to do is a ratio test on this. Now, tell me what we want. Tell me what we want, because I'm asking for what values does it converge. What do I want? I want to set up a limit. As n goes to infinity of a sub n plus 1 over a sub n, right? That's what I want. But for this to converge, right, I want that to be what? Less than 1. This is the big inequality that I have to make sure holds, right? If I can show you that this ratio test stays less than 1, then I can assure you that you're going to get convergence. So what is this for us now? Because now we have x's in here now, right? But it's still this with n plus 1 plugged in over that with just n plugged in. It's still setting up the same sort of ratio. So let's put that in together. That means I need the limit as n goes to infinity. Let's go absolute value. What do you get when you plug in n plus 1 into this? N plus 1 factorial, in parentheses factorial, right? X to the n plus 1. I'll do that next step. That's a sub n plus 1, right? Over the regular one, which is n factorial x to the n. I need that to be less than 1. Notice I'm just restating this each time. Let's try and clean up that limit. N goes to infinity, absolute value. All right, what am I going to do with my n plus 1 factorial because of what I know about factorials and the fact that I see an n factorial down here? Peel off an n plus 1 and then write n factorial next to it, right? That's what this means. Also, I see an x to the n down here, x to the n plus 1. I'm going to break that apart, separate them as x to the n times x to the 1, all over n factorial x to the n. I need this to be less than 1. Good? Cancel. And what are you left with here?
Would you distribute it?
I'm left with limit. N goes to infinity of what? N plus 1 times x. I need that to be less than 1. For what values of x does this converge turns into me asking you the question, for what values of x does this stay less than 1? What do you think? If I plug 1 in here, you're saying 1 divided by it. You go, give me an x value. Someone give me any x value. I don't care what it is. Just give me an x value. Negative 3. Okay, if I plug in negative 3 here, it becomes positive. And then if I let n go to infinity, am I going to be able to keep that less than 1? No? Okay, give me another number. Maybe we go a little bigger or smaller. 1/5. If I put 1/5 in here, multiply times the number that gets bigger, I'm not going to be able to control it, right? As soon as this gets bigger than 5, it'll be 1/5 times your 5. So we go smaller. But the thing is, no matter how small you go, as soon as you fix your x, this thing blows up, doesn't it? And there's no way to keep control over it. So you'll never be able to keep it less than 1. Do you understand that? So this limit right here on the left side, this right here, goes to infinity times x. And there's no way to keep that less than 1. The key is that x cannot be, well, I guess there's one way to keep it less than 1. If x was what? 0. But we already knew that, didn't we? If x was 0, it converged. So the only way to have this right here, this will not happen if x is not 0, right? This will not happen if x is not 0. The only way this happens is if x is 0. But we knew that to start the problem, that if x was 0, it converged. You with me? Yes. You pick any other value of x, you're not going to get this thing to converge. So it only converges if x equals 0. Yes?
If x was 0, wouldn't it be infinity times 0?
Okay, the limit though. If x is 0, I'm not saying x is approaching 0. I'm saying x is 0. When we do, when we got this and we had to bring in L'Hopital and do stuff, it was in the limit. This was getting really big and this was getting very small, but never getting to 0 and actually approaching infinity. The difference is when you're approaching something versus being something. If I let x be 0, because I'm plugging a number into a function, so if I let x be 0, it doesn't matter what this number is. 0 times anything is 0. Good question.
The domain on this would be x equals 0.
And that's it. It's a rather boring function.
Gotcha.
In fact, if you were to define this power series as it was defined in the beginning, and I tell you, graph it, it would be that. That's the graph of it right there. 1 point. That's it.
That's good stuff right there.
That's right. That's a very interesting function. But that gets you in kind of thinking about, how we're going to attack these things. So next question, for what values of x does this converge? Now notice I started at n equals 1. That doesn't make a big difference when we're talking about power series. As long as we continually have things getting bigger and bigger in terms of powers of x keep on going up. Ratio test. I mean, this is the ultimate weapon against these things, all right? So I'm going to set up a ratio test. What do I want? I want the limit as n goes to infinity of the absolute value of n plus 1 plugged into that, right? So 2x minus 5 to the n plus 1 over n plus 1 over 2x minus 5 to the n over n. I want that to be less than 1, right? That's what I want? Okay. Does everyone understand that this is a power series? That could be rewritten as 1 over n times 2x minus 5 to the n. And then to really make it look like what we would want, you could do this. This is a little tricky. Watch. 1 over n, you could do 2 times x minus 5 halves to the n. Is that the same problem? Yes? Just distribute that through. And now this is multiplication. So can I put the n on the 2 and on this one? So this would become 1 over n times 2 to the n times x minus 5 halves to the n. Do y'all see that? And then I can put the 2 to the n over this. And so this is really 2 to the n over n times x minus 5 halves to the n. Does that look more like the power series formula? You have c sub n here, and you have x minus a to the n there. Do y'all see that?
Yes.
Okay. We don't need to show all that. We can just go right to ratio test. I just want to make sure everyone understands that is a power series. All right, what's going to happen on that ratio? Flip, right? We're going to flip the bottom up. Okay. So we get the limit as n goes to infinity. Let's go ahead and do what we need to do here. What can I do with that top piece? Separate it as 2x minus 5 minus 5 to the n, and then what, 2x minus 5, the whole thing to the 1? That's what that is. Over n plus 1 times the reciprocal of the bottom, so the n's on top, and then 2x minus 5 to the n on bottom there, I need that to be less than 1, right? I get cancellation. Nice cancellation here and here. And so now I've got a 2x minus 5, right? And I've got an n over an n plus 1. Yeah? So let's see. Is this the same as limit n goes to infinity, absolute value n over n plus 1 times 2x minus 5? Is that true? Yes? I like to do this. I like to split up the part that's being controlled by n. I like to remove it from the part that's not being controlled by n. And I like to look at that part and just say what happens as n goes to infinity there. L'Hopital, right? You just get 1 here, don't you? So if you take the limit, the only thing left is the absolute value of this, right? Times 1. So the absolute value of 2x minus 5 must be less than 1. Right? That's what's left. So now I just need to know what the hell this means. You know, this is what I need x to satisfy in order for me to have convergence, right? So I'm going to do a quick little reminder. I'm going to come right back to this. Just a quick little reminder of how we solve absolute value equations. Recall real quick. If I say the absolute value of x is less than some number, a, then that means I want to know when x is between negative a and positive a. I'll give you a specific example right here. If I say the absolute value of x has to be less than 4, then that means the distance between the origin and x has to be 4. Right? So like on a number line, here's the origin, here's 4, here's negative 4. My x has to come from anywhere in here, right? So that the distance between x and the origin, that absolute value is smaller than 4. So I can be on either side of 0, right? But that's the same as saying that the x has to be between negative 4 and positive 4. That's what this is. So what you essentially do is you drop the absolute value and insert the opposite on the other side. Do you see that? That's what you do. So when I'm back over here and I'm trying to solve this, I have the absolute value of something has to be less than 1 is equivalent to me saying 2x minus 5 must be less than 1, but also bigger than negative 1. Now we have kind of like a compound inequality, two together here. Solve for x. So if I asked you to solve for x, just in this one, if I asked you for solve for x, what would you do? Add 5 to both sides. If I asked you to solve that one, what would you do? Add 5 to both sides, right? So on both of them, you can solve them simultaneously. Add 5 all the way. So add 5 here, you get 4 less than 2x. Add 5 over here, you get 6. Y'all got it? Mm-hmm. Divide by 2. When you divide inequalities by numbers, you have to be careful, because if you divide by a negative, it flips, but we're dividing by 2, so it doesn't flip. So this is just going to become, what, 4 divided by 2 is 2. X less than, what, 3? That's it.
So it's
It's between
between 2 and 3.
2 and 3. This right here, this is the domain of the function. If we were to graph this function, this power series that we started with, the graph would only exist between 2 and 3. Do you understand that? Are you sure you understand that?
Yes.
All right.